So like we did with linear equations in one variable, stepping up to linear equations in two variables, aka lines, aka linear functions, we can take all that stuff about having quadratic equations in one variable and saying, you know, instead of having equals a number, what if we had a y equals? And as it turns out, those are also functions. So a quadratic function is going to be any function that could be put into the form f of x equals ax squared plus bx plus c. The a and b and c's are numbers. They have to be real numbers, and a is not 0 because that would not be quadratic anymore. That would be linear. So there's a different version of that, though, that is useful for a different purpose. There is what we call the vertex form, and that has the f of x equals a, so that still shows up, but now parentheses x minus h parentheses squared plus k. Now if we look at the difference between those, we say, hey, from our quadratic equation stuff, completing the square seems to be happening here, and that's exactly the deal. So we could take our completing the square skills and we could retool them to apply to these quadratic functions. So here's an example where we've got that laid out. We said, okay, we're gonna have, well, that's nice that there's just a 1x squared. So we're gonna take that number in between the x squared and the x. We're gonna divide that by 2. That gives us here a -4. We're going to take that number, we're going to square it. That gives us a 16. And we're going to want to, well, we originally said add the 16 on both sides, but we don't want to mess with the function notation here. So we're going to retool that, comment, and say that the 16 is not going to be added on both sides anymore. It's going to be added and subtracted on the same side. So we're still preserving the balance by adding and subtracting on the same side. So we'll put the plus 16 with our x squared minus 8x, and we'll put the minus 16 at the very, very tail end of things. Now that first trio of terms will end up becoming that perfect square, where again, we're gonna see inside the parentheses, after the x, we get that special number that we had gotten from the beginning of our completing the square steps, where we had that -4. So x with the -4 in that light blue color, parentheses squared. Outside of the parentheses, we can simplify those and get a -15. So what we have showing up here in comparison to that standard vertex form, a, the number out in front of our parentheses, is a 1. X minus h, x minus h, x minus 4 is the h number, and then the k is all the way at the tail end, so the k is this -15. Talk about what that is in a minute. Let's look at another example, one that is different because it has something other than the a equals 1. Now we're going to start out in the same sort of fashion as saying, I want to worry about the x squared and x stuff, but because I've got a 2 out in front and I don't want to try to rearrange things, I want to keep that function notation, I've got to do another bit of retooling and say, let's take that 2 and factor it away from our variable terms. Let's take that 2 and factor it away from the x squared and away from the x. That means that what we get inside these parentheses now has this plus 10. So we'd be using that plus 10, dividing by 2, getting that plus 5 in light blue, taking the plus 5 and squaring it, and getting 25. Now we've got to do our little balancing act. We're going to take the x stuff, and we're going to put in a 25. But it's very important for us to be paying attention to what's happening here, because when we put in that plus 25, we have also now got this 2 that's playing a role. Overall, we just put in a plus 25 times 2. So that 2 is playing a role. Let's give that a little bit of kind of recognition there, a little underlining here. That 2 is playing a role. So what we have overall added at the moment is this 25 times 2. If our new version of things is that we're adding and subtracting on the same side, out at the tail end, we're going to want to balance things based on the 25 and based on that number from out in front of our parentheses, which is the 2. So that balancing act is meaning that we'll have to subtract a 25 times a 2. Now we are in a position to then say, okay, well, the 2 is still staying out in front. What's going to happen inside those parentheses? Well, we know that there's that little shortcut relationship we can use. After the x, there's that light blue number with the plus 5. So that's going to be showing up inside of our set of parentheses. And then at the tail end, where we've got some simplifying we can do, that's going to give us that other part that we would need. And so, in this particular example, comparing this to that vertex form, the A is equal to 2. The H number, well, we're going to take this X stuff and we're going to change the sign on it. So instead of positive 5, that's going to be a negative 5 for our H number. And our K number is going to be that number at the very tail end, which is that negative 48. So again, just a quick note, the A is equal to 2. The H number is the negative 5. And the K number is the negative 48. So vertex form, by name, means that something about this information is going to correspond to something that we would refer to by the name vertex. So that vertex is one of our characteristics here to worry about. So what we have happening, we got 2 different possibilities with how this parabola shape, which is the name that we call the graph of our quadratic function, we got 2 different ways that that parabola shape can appear. It can appear in what we call open up, so that it is growing upward, or open downward, where it is growing downward. And that's going to be based on the A number. If the A is a positive, our parabola opens up. If our A is a negative, our parabola opens down. So far, those 2 examples we've looked at have both had A values that are positive. So both of those, if we graph them, doesn't matter if we graph the one that they originally gave us or if we typed in the vertex form, they would both show us a parabola that opens up. But what about that vertex? Well, that vertex is going to be a point h comma k. So the h value and the k value that we were getting, and here's this most recent example, the h value, negative 5. The k value is negative 48. If I pair those up, that's going to be the lowest point, because that one opens up. It's going to be the lowest point. If our parabola opened downward, then that particular point would be the lowest point, or excuse me, the highest point. Got that turned around. That would be the lowest point versus the highest point of our parabola. So opens upward, lowest point, opens downward, highest point. That's going to be that h comma k. There's that vertex right there at the top or at the bottom. And so then there's this other element of, and I certainly don't blame you, complete the square, boo. Well, let's save ourselves some time and trouble. Certainly, if we are expected to complete the square, we must. But if we are not expected to do so, or if we are simply given our own choice, we can instead find those values in a different way. And you might feel that this is a much quicker way to do so. We've got our h coming from a formula. H is equal to negative b over 2a. Then the k, well, once I have the h number, I can take that and plug it in to my function and get the k number that we need. So we've got a nice way that we can work out those values instead of having to go through the completing the square method. We still want to be familiar with it because completing the square is a handy tool to have at our disposal for various purposes and at various times, like later on in the future for, say, pre-calculus algebra or other times. But if we go through and, hey, it's that same thing again. That's that function that we just had. We should be expecting to get that h is the -5 and the k is the -48. Let's check it out, right? The h formula, h is equal to -b/2a. The b number is 20. The a number is 2. So if we put that into the formula, ba-boom, yep, there's that -5. We want to take that -5, we want to plug it into our function in order to find the k number. So we want f of -5, and if we go through the number crunching for that, yep, there's that -48. So the vertex that we've got in this particular case is going to be the point -5, -48. And just as a little quick extra note, we had mentioned this, but let's put it in writing. The a value is positive. That means that this parabola opens up. Because this parabola opens up, that means that the vertex we just made note of is officially the lowest point. Lowest point. Just for something a little bit different, notice that in this next example, our function starts out with a -3x squared, so finally we get a little bit of variety there by having that negative number show up. But again, h comes from this formula. H is equal to -b/2a. The b number is our +24. The a number is the -3 of that function. So we put those values into that formula, crunch that out, and we get h is specifically +4. We want to take that number 4 and put it into our g function so that we can find the other half of our vertex. So if we do g of 4, that's going to end up cranking us out this k number, and as it happens, that's going to end up being an 18. So our vertex is specifically the point 4, 18. And again, let's make a real quick side note here. What's going on with that vertex? Can we be a little bit more specific about that? Well, sure we can. So we have the a value that we commented was a negative. So that would mean that this parabola opens downward. Because this parabola opens downward, that would then mean that our vertex is officially the highest point. So 4, 18 is the highest point on that parabola that we've got. If we take a closer look at what's going on, and also bring in a little bit of our equation solving skills from earlier, we can get some other information that we might find helpful. So bring in a little bit of our basic discussion about functions. We had that notion of maximum and minimum. So if we bring that back up again, the k, the y value of the vertex, is going to be either the minimum or the maximum, depending on how that parabola opens. So open up, our k value is minimum. So open down, then our k value is a maximum. Our parabola also happens to have some symmetry, but if we pick that sucker up and move it, it's not necessarily a symmetry about the y-axis, but we can still cut that sucker in half. So there is an axis of symmetry, a vertical line, hey, that not coincidentally, passes right through the vertex. So x equals h. H doesn't only help me find the vertex, it also helps me find this axis of symmetry, this vertical line, x equals h. That's going to cut our parabola into mirror images, left versus right. Doesn't matter if it opens up or if it opens down, still cutting things in half, mirror images. There's always going to be a y-intercept. That's just one of the nature of the quadratic functions. But when it comes to going, well, quadratic functions equal to 0, what could happen? Well, we might not get any real number answers because we might get complex conjugates. So we might not have any x-intercepts. We might get only one solution, like officially it's repeated, but only the one point, so only one y-intercept could show up. Or what we are much more used to, because it happens much more often, is that we would get two solutions, but those could be real numbers, and real numbers could correspond to x-intercepts. So as far as our parabola goes, depending on how it appears with respect to our x-axis, there might be two x-intercepts, there might be only one x-intercept, there might be no x-intercepts. Just to kind of wrap some of that stuff together and put a different spin on our vertex information, let's look at an example here that asks about intercepts, max or min value, and the axis of symmetry. So we can start with stuff that we are already familiar with, and we might want to start with the least amount of effort. The y-intercept out of all of these things is the quickest for us to find, because plugging in 0 for x is a nice quick thing for us to accomplish. So if we plug in 0 for x and we get a -7, then that would mean that we would be talking about a y-intercept 0, -7. Using skills that we had been talking about before, where our x-intercept would come from having that equation set equal to 0, solving that equation, that one factors, take each factor, set it equal to 0. One of the answers that we have is x equals -7. One of the answers that we have is x equals 1. That means that we do have two x-intercepts showing up here, and they are specifically -7, 0 and 1, 0. Then bringing in more of the new stuff, the axis of symmetry is based on the h number, so we'll crank out the h number. The b value in this particular equation is 6, the a value is 1, and so that means that our h ends up being a -3. Our axis of symmetry is a vertical line, so x equals -3 is that axis of symmetry. I need that to figure out the max or the min value, because the max or the min value comes from the k. So the k is going to be giving us that value, but we need to know which is it, max or min, because this has a equals 1, that's positive. The vertex would be a minimum point. That means the k value is a minimum value. So if we calculate that k value, we want capital F of -3. So if we crank that out and get a -16, that means that officially speaking, our minimum is -16. If they had asked us for the vertex, we would also then say, okay, the vertex is -3, -16. That's fine. But they didn't. They put a little spin on it. We still needed the vertex information, but we needed it so that we could report the axis of symmetry, and so that we could report whether we have a maximum or a minimum value and what that value actually is. remember that we had talked about the phrasing of things as far as this maximum minimum business. We have a minimum. It occurs at x equals -3, but the minimum value is -16. Just to give you a little taste at the moment of how something like this might be somewhat useful, with the understanding that this is a bit of a contrived kind of situation. There are plenty of other ways that quadratic functions are useful. I'll mention a couple of them here after we've finished this example, but just to throw in a little bit of geometry stuff that we've got that can tie in with our quadratic functions. If we've got to fence in an area and we don't need any fence that's along the river, then we're going to get a rectangular enclosure that looks like this drawing here. We've got a width, we've got another width, we've got a length of fence. We do not need any fence along the river, so we only have those 3 sides that we have for our fencing. And if we've got a certain 1,600 feet of material to use, how big of an enclosure can we make? So how big of an enclosure refers to the maximum area. That means we need area, and the basic area comes from length times width. But that's got 3 variables in it: area, length, width. We can't hack that unless there's a way of being able to transform that area into something that has only length or width. Well, we only have a certain amount of material that we can use. We have to use all of it in order for this enclosure to end up having the maximum area. So we've got to use all 1,600 feet between our length and our width and our other width. This is most quickly rearranged to give us L equals. And now we can replace the L in our area formula and get an equation that has only the W showing up in it. But the way that this looks is not like our other earlier quadratic functions. So if we rearrange that so that the -2w comes out, -2w squared comes out in front, now we can say, okay, the A value is a -2, the B value is a 1,600. If I'm worried about max, I'm worried about vertex. If I'm worried about vertex, I'm worried about the H, and the H in this case is a width. We don't want to lose sight of that. It's coming from the formula -b over 2a, so -1,600 over 2 times -2, which would mean that we get a 400, and that's measured in feet, so 400 feet. Now we don't necessarily need to worry about the K value because the K value is the maximum area. We're asked for what are the dimensions. Well, there's the width. Width, 400, 400. What's the length? Well, we've got that relationship that the length is going to be coming from the 1,600 minus 2w. So 1,600 minus 2 times 400 gives us a length of 800 feet, so that largest possible enclosure, that largest possible pen, spell it right, huh? Is 400 feet by 800 feet. Now, I'm sure a lot of y'all are going, even if I owned land and had it butt up against a river and had to fence some stuff in and all of these other ifs, I'm probably just going to go, I want to make it a particular size. I will buy the fence that I need. I am probably not going to be hamstrung, have my hands tied by going, oh, I only have a certain amount of fence that I've inherited? Psh, give me a break. This, you would very reasonably argue, is not a super useful version of quadratic functions. So what is? Well, space fans, rocket launches, war fans, bullets, tank shells, Hawkeye fans, arrows, projectiles, anything that is projected like bullets and arrows and tank missiles and rockets, those things are going to follow a parabolic path. They are going to fit the quadratic function. Got some sort of A's and B's and C's, we could model that motion and we would see that quadratic sort of behavior. One of the other things, for those of you who like to be able to see at night and might, instead of using your cell phone, have an actual flashlight, you have behind that flashlight bulb this lens or this reflective surface, and that reflective surface happens to also be a parabola shape. So you do have some realistic uses and connections with the quadratic function stuff. It's certainly much more practical than this example here might suggest. But we do have those other sorts of considerations, and you might find others as you are doing your exercises.